So this is a rational number, and this is a rational function. A function divided by a function, a number divided by a number. Rational number, rational function. Now these rational functions can be really difficult to integrate unless you split them up into a few different fractions. Now in order to do that, we need to consider a couple of different cases. The first one is proper rational functions. That is where you've got a function divided by a function, but the one on the top has a smaller degree than the one on the bottom. So an example of a proper rational function, here it is here, a linear function divided by a quadratic function. So degree 1, degree 2, that's proper. If I change it slightly and make it 2x squared plus 5 over x cubed plus 3x minus 4, this is still proper because this is degree 2 and this is degree 3. So look at the leading coefficient. Of course, you can probably guess there's improper ones as well. Let's look at them. These are improper. You can see this is improper because degree 3 on the top, degree 2 on the bottom. But this is also improper because they both have the same degree. So we're only interested for the moment in proper ones, and proper rational functions have a lower degree on the top than on the bottom. So some rules to follow when doing this, right? If we have a number on the top or a linear function on the top, and we have a quadratic on the bottom, we've got it in factorized form here, we can write it as a over 4x minus 9, the first linear factor, plus b over 2x plus 5, the second linear factor. Now I've just taken away the numbers there and generalized it. Now remember, g of x needs to either be just a number, the number 5, or some linear function, ax plus b. It needs to be smaller than the thing on the bottom, and the thing on the bottom here is a quadratic. And then we can break it up into the factors. Alright, well let's try something that uses that rule. We're going to learn another couple of rules as well, but let's do something that uses that. So first example here, we're going to take this and we're going to resolve it into partial fractions. We're going to cut it into two fractions here. Now you might be looking at it saying, wait, it doesn't look like that, but it's a quadratic, so we can easily split x squared plus 2x minus 3 into two factors. So now that we've factorized and split it into two factors, we can write it just like this. Now that a over, we can use this factor here, x minus 1, plus the next one, b over x plus 3. Alright, and you might be looking at this going, okay, well this is fine. We're using the denominator bits, but we haven't considered the 3x plus 5 on the top. And that's what happens in this next step. Because now what we do is behave like we want to add these two fractions back together again. If we want to add these two fractions back together again, the easiest way to do it is to multiply the numerator by x plus 3, the numerator by x minus 1, and put them all over a single denominator, x minus 1 times x plus 3. So this is me 3 years in the future correcting this video. So from here past, Joel Speranza does something really silly. He does this. Now the problem here, of course, is that x minus 1 and that x plus 3, they're in the wrong places. It shouldn't look like that at all. So let's correct it. What we really need is something more like all over x minus 1, x plus 3. And then the question we ask ourselves is, what do I need to multiply a by to make it have this denominator? And the answer is x plus 3. So we get a times x plus 3. And we get b times, and what do we need to multiply that fraction by to get it over this denominator? X minus 1. Alright, so that's what should have happened from here. Alright, I'm going to take over this example from here, and then I'm going to pass you back to past Joel. So, what have we got now? We've got 3x plus 5 over this here is equal to a over this over the same denominator. Notice the denominator here, x plus 2x minus 3, is equivalent to x minus 1 times x plus 3. So if 3x plus 5 over that is equal to that over 3x plus 5, then the numerators must be equal to each other. So we can now ignore that x minus 1 to x plus 3 and just say that the numerator, a x plus 3 plus b x minus 1 is equal to the numerator at the beginning, 3x plus 5.
Okay, so now we know that 3x plus 5 is equal to a times x plus 3 plus b times x minus 1. It still feels really problematic because we only have one equation and three variables that we don't know. We don't know what x is, we don't know what a is, and we don't know what b is. So what do we do here? Well, remember, this is a function. And so in functions, our x's can be any values we want, right? If you've got a function that's like a parabola here, x can equal 1, x can equal 2, x can equal 3, x can equal all these things along here. So we can sub in any value for x that we want if it's convenient. And I can see two values that I can sub in for x that would be very convenient for me to sub in. I'm going to sub in x equals -3. And you're going to think, why would you sub in x equals -3? Well, it becomes super obvious when we sub it in. We get a -3 plus 3. I've just subbed in -3 here. That's going to become 0. And this a is going to vanish. 0 times a is 0. Plus b -3 times minus -1 is equal to 3 times -3 plus 5. All right, 3 times -3 is -9 plus 5 is -4. -4 equals -4b because this cancelled out. It's gone. 0 times a, 0. So -4b equals -4. So that means that b is equal to 1. Fantastic. We now know what b is. What about a? What's a? Well, we can do the same trick again, right? There's nothing stopping us from just essentially doing the same thing, but instead of subbing in x equals -3, we sub in something else that's convenient. I subbed in -3 because I knew that -3 plus 3 was 0. If I want to get rid of this b here, I'll sub in +1. If I sub in 1, sub x equals 1, I guess is a better idea. Sub x equals 1. Let's do that. 3 times 1 plus 5 equals a 1 plus 3 bracket plus b times, and 1 minus 1 is 0. That's going to be 0. Okay, actually, let's put it in there. All right, but that is going to be 0. So now we have 3 times 1 is 3 plus 5 is 8, and a times 4 is 4a. So a is equal to 8 divided by 4, which is 2. So we have finished. We're done. We're at a final answer now. We have resolved this function here, 3x plus 5 over x squared plus 2x minus 3 into two fractions. And those two fractions, let's do it down here. Therefore, 3x plus 5 over x squared plus 2x minus 3 is equal to two fractions. And the first fraction is over x minus 1. And the a value is 2. So 2 over x minus 1. Plus, and what was our b value? Our b value was 1 over x plus 3, or I guess x plus 3, right there. Okay, that's what we've done. We've resolved it into partial fractions. We have a rational function here, and using this process, we can split it into two fractions, 2 over x minus 1 plus 1 over x plus 3. Of course, if you don't believe me that that's true, you can just like sub in a value for x. You can sub in like 2 here, 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 and here. And of course, the left-hand side should equal the right-hand side. Now, that's not the only partial fraction rule we have, and I'll pass you back to Joel to show you another one.
New formula, g of x equals cx plus d squared. So a linear function on the bottom squared. That's going to result in that same linear function, not squared, plus that same linear function squared. All right, so compare and contrast here. Now we're going to do a worked example here. we're going to do a worked example where we kind of combine these two ideas together. So here's our question, and you can see it's got a few things going on here. Some function on the top, but just degree 1. And now we've got a function on the bottom that's degree 3, because it's a squared here and a thing here. If we expanded that, we'd have an x cubed there somewhere. All right, so looking at this first bracket, this x plus 1, that looks a lot like this top one here, this ax plus b. So that's going to result in this bit right here. So far so good. We've got a over that x plus 1. Now, this x minus 1 squared, that's going to follow this rule here, which means that we're going to have just the linear term on the bottom, and then we're going to have to also have the linear term squared on the bottom. So we're combining our two rules here. We have a linear thing on the bottom here, which gives us our a, and then I'm using b and c here because I've already used a. So instead of using a for the linear term on the bottom, I'm using b. Instead of using b for the squared term on the bottom, I'm using c. Now that we've got that, it's time to push all of these together again into a single fraction with a common denominator of x plus 1, x minus 1 squared. That's what it's going to look like. Now, it's a little bit hard to keep track of, right? So a over x plus 1, to make it have this denominator, we would need to multiply top and bottom by x minus 1 squared. To have b have this denominator, we would need to multiply it by x plus 1, and then one more lot of x minus 1 to have that. And c, we just need to multiply top and bottom by x plus 1 to give us that same denominator. Now, when it comes to partial fractions, this step, because the next step I'm going to do is say, well, if the left-hand side is this over this, and the right-hand side is this over this, then the numerators must be the same because the denominators are the same. We do this so often with partial fractions that we don't have to do that. We can just kind of skip the step where we show the denominator and jump straight to this. Numerator equals numerator. Alright, so we can pull the same sorts of tricks. If we let x equal 1, 1 minus 1 will be 0, so the a will disappear. If we let x equal 1, 1 minus 1 will be 0, so 0 times that. The b will also disappear, and we'll get left with just a c value. So let x equal 1, we get this, which is 12 equals 2c, which means that c equals 6. So now if I let x equal negative 1, that should pull the same trick. X equals negative 1, the c is going to cancel out. X equals negative 1, that bracket's going to become 0, which means the whole thing becomes 0, and I'll be able to figure out what a is. So let's let x equal negative 1. So when we do that, what do we get? We get negative 2 plus 10 is 8, and then we have negative 2 squared, which is 4. So we say that that's 4a, which means that a will be equal to 2. So I know what a is, I know what c is, I need to figure out what b is. Now just switching colours so it's easier to see, this is the same equation that's written all the way back up here again, but we have new information. We know that a is equal to 2 and we know that c is equal to 6. That gets us a little bit closer because now we just have an x and a b that we don't know. Now x can be literally anything. We can shove in anything, 1,000,000, 2,000,000, negative 1,000, whatever. Let's put 0 in for x and then we'll be able to find out what b is. So that's what it looks like. We've got 10 equals 2 minus b plus 6, and we can solve that for b now, and b is going to be negative 2. We are finished. We can write this now as this full partial fraction. Complete solution, 2x plus 10 over all of that is equal to all of this, a, b, and c values there.